Hey everyone, Geophysicist Stefan Burns here. We have just made a groundbreaking discovery within our solar system, specifically from the asteroid belt, and this is going to rewrite our understanding of mechanisms in play within our solar system and also our larger celestial environment. This discovery was made by the Vera C Rubin Observatory out of Chile, and what they found were super fast and ultra fast spinning asteroids. We have known about this spin limit for asteroids in the main asteroid belt and also other populations for a while, and that is 2.2 hours for the main asteroid belt. And basically what that means is we really haven't found that many asteroids spinning faster than 2.2 hours for one complete rotation on their axis. This is a little odd. This doesn't really apply to the tiny asteroids like, a meter, 2 meters across. We're talking about the bigger asteroids, half a kilometer or more. They seem to fall up against this spin limit. Well, the Vera C Rubin Observatory went online in 2025 and started taking some pictures of the sky. We see the location of where they were surveying when they found these super fast and ultra fast spinning asteroids, and we see the Virgo cluster and some other parts of the sky here. They're taking big surveys of the sky multiple times per night, getting a lot of data. Then, since it's such high resolution, they can do some really advanced mathematics and calculate light curves, perform Fourier transforms, do some really cool stuff, and do it at super high precision. So they found a bunch of objects across this time frame. It's just like a couple weeks along the main asteroid belt, some near-Earth asteroids, Apollos, also some trans-Newtonian objects. They're expecting to find millions of objects over the next few years and, let's say, decade. This is asteroids, comets, supernovas, even perhaps Planet 9, Planet X. So really exciting stuff out of Chile with the Vera C Rubin Observatory. Well, they found these super fast and ultra fast spinning asteroids that broke the spin limit. And some were spinning even at rates of one rotation in less than 2 minutes, which is phenomenal. And that is a big clue, perhaps, as to some of the dynamics at play with Interstellar Object 3I Atlas, because we can apply some of our other astrophysical knowledge in terms of how jets are produced, astrophysical jets, as it relates to 3I Atlas, because astrophysical jets, these jets of ionized matter that extend out, we see them from galaxies, we see them from neutron stars and from supernovas and black holes and such. They are typically produced when you have a central magnetized body that is spinning rapidly. So a rotating central magnetized body is able to produce astrophysical jets. And we've been seeing a ton of anomalous jet activity from Interstellar Object 3I Atlas, and it's had its sunward facing jet, all these jets being tightly collimated, meaning that they're not dispersing out that much. They are staying very tightly compact and extending out tremendous distances, just like we see with astrophysical jets from, let's say, like Galaxy Centaurus A or Galaxy M87. So, well, what could explain that? Well, if 3I Atlas, its nucleus, is magnetized and it's rotating rapidly, similar to these super ultra fast spinning asteroids, that could give us an explanation for the production of these jets, because that magnetic shear from the rotation of that central body would then allow for these complex magnetic field structures, which allow for the ejection of plasma. It also generates plasma. That whole rotation aspect generates plasma. We see that with the sun. We see that with Jupiter. We see that with the Earth, the outer gas giants. They are all central bodies that are magnetized, that are rotating, and they have plasmaspheres to them. So this is a really exciting discovery out of Chile. And let's just look at some of the main asteroids that they found. We have 5 main spinners here. 2025 MV71, a big asteroid, 900 meters in diameter and a spin period of 13 minutes. You can take most of these values here pretty accurately because their error rates on them are very low because of just how precise the data is. So this is super cool stuff. 2025 MN45, estimated diameter 710 meters, spinning once on its rotation axis in less than 2 minutes, 1.88 minutes. This is one of the fastest ones found, along with 2025 MJ71 spinning at less than 1.92 minutes, 120 meters in diameter, so quite a bit smaller than 45, but still a large asteroid. You would not want that to hit the Earth. And this is a near-Earth asteroid as well, so this one does get close to the planet. We also have 2025 MG56, has an estimated diameter of 660 meters, a spin period of 16 minutes, and then MK41 with a spin period of 3.75 meters at a size of 540 meters in diameter. So these are big asteroids spinning very fast. They break the spin barrier dramatically, not just by a little bit. Oh, they spin once every hour. No, dramatically, less than 2 minutes for some of these. And then this shows that they are made up of materials that are able to resist the shear forces from that intense angular velocity momentum that is, of the object itself because it's spinning so rapidly. So in the paper that was released for this, which is linked in the video description, I recommend you read it yourself. It's interesting. They talk about these asteroids being made up of clay or rock-like materials, but also metal, of course, would fall in there. And that would have enough tensile strength to keep these things together. Because a lot of asteroids are actually kind of like loose clumps of smaller little planetesimals and material, and they're held together by gravitational forces, but they're not that strong, and or electrostatic forces. And if you have a fast enough spin on them, it would just kind of fling these things apart because they're not really that cemented together, though the bigger ones are. But you need a high enough bulk density to these things for them to hold together. Because if there's a lot of volatiles like water and ice and things of that nature, if it's spinning really fast, it's just going to go off like this. Here we can see these asteroids, these 5 asteroids in particular. I plotted them here, and you see that they're all in the same part of the sky because that's where the Vera C Rubin Observatory was looking in 2025 for this. This is just some of the first initial data coming out, so expect a lot more groundbreaking discoveries from that telescope over the next, not even years, but next few months. Honestly, it's going to be really, really cool. Fully coming online in 2026. And so you see that they're all main belt asteroids, various inclinations and eccentricities to their orbit. Nothing super, super crazy. And what we see is that you get these jets formed by these centralized spinning magnetized bodies. And so if we can look here, we see an entire galaxy producing astrophysical jets. This is Centaurus A here. And you see those massive jets coming off of it, which is really quite mind-blowing to think about the scale of this. I mean, this is an entire galaxy, but there are processes that exist at that scale, right? This is hundreds of thousands of light years. There are processes at that scale that create these jets. And so this shows that this is some base physics of our reality. If you have, this galaxy is rotating, right? And in the core, you have a lot more stars and maybe some black holes. And they're rotating themselves, and at a smaller fractal scale, they're producing many of the same phenomena. But it's highly magnetized, and that's causing the ejection of this matter out in all directions. We can also look at galaxy M87, which is a classic example of this super tightly collimated, very, very long astrophysical jet moving near relativistic speeds, and there is the central part of the galaxy, like the core of the galaxy. So when you have these central bodies that are rotating and they're magnetized, you can produce these sort of jets. We also see that with the Crab Nebula. Here we'll look at it in a variety of different wavelengths of light. So this is radio wavelengths. This was produced by the supernova in 1054 AD. So SN 1054, here we're looking at the Crab Nebula in infrared now. And at these lower wavelengths, these lower frequencies of light, we don't see the jets. We just see kind of the shock waves. But as we go up, this is now optical via Hubble, we will start to see these jets. And it really shows up nicely in the X-ray wavelengths. So check this out. When it goes to X-ray, well here, ultraviolet, we can start to see a little bit of the jet activity in the central core there. This is taken by Newton. But once we get to the Chandra data, you'll see this jet there from the center of where the supernova occurred. So it even actually has like the Birdman shape, which is really interesting in my opinion. But we have this central body, and then we see that jet emanating out. So we see this everywhere across the universe at large scales and at small scales. And maybe we just saw it at the smallest of scales with Interstellar Object 3I Atlas. Here we can look at some recent data via Hubble processed by Tony Scarmato, and we see 3I Atlas on the 30th of November. We also see on the 27th of December. We have new data from January 7th we're going to look at as well. He applied a processing filter to this to remove any circular features, which would be the coma that is surrounding 3I Atlas, which has this roughly circular shape. So if you're able to remove that, you can pull out these fainter details which are not homogeneous. And so we see on the 30th of November, 3 jets, this one by far being the strongest. But then if we go over to December 27th, we see how they change. And now we have 3 basically equal jets and roughly spaced 120 degrees apart. This is quite bizarre. It's not like we never see jets on comets or tails on comets or stuff, but in general we don't see them like this. And we have to remember, comets in our solar system, as far as we know, they're very, very low in their bulk densities, mostly like water and volatiles and just like methane and CO2 and stuff. There's really not much to them. I mean, there's a little bit of metal and such, but in general, they have a very low bulk density. If they're spinning quickly, they're going to shear apart. So for an asteroid that is mostly metallic, you can have it break that spin limit. But for a comet, you're not going to get that. Interstellar Object 3I Atlas seems to be quite a bit different. Here we see more data processed by Tony from January 7th of this year, 2026, and we see the sunward facing tail. Very tightly collimated, going in the sunward direction. Very, very bizarre. It's had that both going towards the sun and then also leaving the sun. Both times we've had this sunward facing tail or this anti-tail. And if we look at some more processing by him, same data set, we see again more jets appear, not just the sunward facing tail, but other jets surrounding the nucleus of Interstellar Object 3I Atlas. So the missing puzzle piece, and I've been thinking about this for a while, and this new data out of the Vera C Rubin Observatory coming out just in the past couple days finally helped me to like really see the full picture, and that's why I'm relaying to you, is that it appears to me that 3I Atlas is magnetized. And I've talked about this before and how certain astrophysical processes can actually produce magnetite, especially in the interstellar environment. You can get the natural production of magnetite, which is magnetic. And we see this enhanced amount of nickel with Interstellar Object 3I Atlas. And if there's iron and all this stuff, it could be magnetized. Maybe it's highly magnetized. We don't know what it is, whether it was produced like a comet in our solar system at the outer edge and then flung out, or maybe it was a part of an exoplanet and it's actually part of the magnetic core. A planet got ripped apart and flung out, and we're actually seeing a highly magnetized body. And well, if it's traveling at speeds of 60 kilometers per second at perihelion, closest to the sun, 68 kilometers per second, that's incredibly fast, the fastest ever object observed. Who's to say it's also not spinning incredibly quickly? We have data on the rotation period of about 15 to 16 hours, but a lot of that data is because the coma is super, super opaque, and I'm not sure how easy it is for us to see brightness variations, changes in the apparent magnitude of the actual nucleus of 3I Atlas when it has such a thick, dense coma. And also because we are seeing this sort of jet activity, that's also going to obfuscate whatever we're seeing. So it is possible that 3I Atlas is rotating faster, and that would be an elegant explanation as to how it's able to produce these tightly collimated jets. Now, a couple interesting things to speak about as it relates to this. I have the book Evolution of the Solar System here by Hans Alvin. Fantastic, fantastic book. on all this stuff. This guy was way ahead of his time with the limited data and observations that he had. The formation of satellites around a planet and the formation of planets around a star cannot take place unless the central body is magnetized. A reasonable model is that of a rotating magnetized central body surrounded by a network of prominence-like structures joining the surface of the central body with a surrounding plasma. The moment you have gas in space, it becomes at least partially ionized. Dust also takes on a charge. Boom, you have a complex dusty plasma. We know that 3I Atlas is surrounded by a complex dusty plasma. If you have this rotating magnetized central body, it's going to be joined to that complex dusty plasma coma by these prominence-like structures, and that helps there to be a transfer of angular momentum and energy from the central body to that complex dusty plasma cloud. The transfer of angular momentum is achieved through processes in this plasma. There is a system of strong electric currents flowing in the plasma, which results in filamentary structures. They stretch out from the surface of the central body to the most distant regions, and the filaments have a density that is orders of magnitude larger and a temperature that's much lower than those of the surrounding medium. Well, I mean, we're basically seeing that in real time with 3I Atlas. And we have this data not only in our solar system. We see that the sun is a magnetized body central to our solar system, rotating with the planets around it. Then we see, for example, with Jupiter, it's a central body that is highly magnetized with its satellites rotating around it. We see this with galaxies where there is a central galactic core that is rotating, that is magnetized with stars and other structures around it. And so we see that this is a base physical property of our reality and our universe. And so that begs the question of, with 3I Atlas, if this is a central magnetized fast rotating body, and it's magnetized because it's mostly metallic and therefore it's able to resist these immense shear stresses involved with rotating quickly, and its dusty plasma coma, it literally could be like a microcosm environment of a solar system being birthed, which is really interesting to think about, and how there could be tiny little ultra tiny, not even planetesimals, like embryos being developed within its coma, its dusty plasma coma, where you are having this aggregation of material, and it passing through our solar system highly energized it and sped up all these processes. So if things are fractal, and we've seen 3 good examples, right, going from the galactic scale to the solar scale to the planetary scale, who's to say that we can't have this happen at a smaller environment as well, given the right characteristics, which is spin, which is magnetization, a large central body, and also, plasma processes. So that is what we're seeing right now in our solar system. And I think that is a big clue as to what's been happening with 3I Atlas. We can look at some examples of the spin period for these asteroids that were discovered. This animation roughly shows the correct spin period because they're rotating slow enough that some of these are probably spinning about once every 2 minutes. So that is a visual example right there of what we are seeing in our asteroid belt, though these are much closer spaced together than they are in reality. The asteroid belt is actually very low density, especially compared to the distributed densities of the planets and their orbits. So there's very little mass in the asteroid belt, but most of it is congregated within the dwarf planet series, and there is active accretionary processes that are taking place within the asteroid belt. And so, well, we've been seeing a lot of interesting things occur within our solar system recently, especially with the flyby of 3I Atlas. And it checks off a lot of boxes and answers a lot of questions if we have the assumptions of 3I Atlas being magnetized and spinning quickly. How fast, I don't know. And whether it is magnetized or not, I don't know. But we have discussed that before. There is evidence of in situ magnetite production due to natural space processes, especially in the interstellar environment. And so I think it's likely that 3i Atlas is magnetic. We've seen how there's been a strong connection and correlation between solar activity directed towards 3i Atlas and also 3i Atlas, with big sunspots rotating into view of it, and then boom, we get solar storms launched towards it. That was really occurring quite remarkably around its perihelion, its closest approach to the sun, and also in the months afterwards. That effect seems to have died down recently, but as it's been moving further and further away. But if this is very magnetized, and that can make sense. We also know that just in general, comets are magnetized because of all the gas and dust that they produce. It ionizes, it creates an ionopause, a magnetopause around the comet. And if there's a big solar storm impact, that magnetopause can go from strengths of like 50 nanotesla up to like 300 nanotesla. So if the central body is already magnetized as well, it could get a lot stronger. Earth's magnetic field is 23,000 to 67,000 nanotesla approximately from the low to the high. And if maybe 3i Atlas has a field of 1,000 nanotesla, 2,000 nanotesla, that's very strong. Mercury's magnetic field is 1/100th the strength of Earth's, right? So if you have 3i Atlas getting up to 1,000, 2,000 nanotesla because it's centrally magnetized, perhaps even greater, then that could really affect the electrodynamic circuit of the solar system. I think that's exactly what we're seeing now, and it's flying close to Jupiter in March, just outside of its hill radius, which is where Jupiter has a strong gravitational effect. But we're ignoring electromagnetism if we're only speaking about gravity, and electromagnetism is so much stronger of a force than gravity when it is active. So this March is going to be very dynamic, I think, as a result of Interstellar Object 3i Atlas flying close to Jupiter. We'll have to wait and see what happens then, but I'm not just immediately ruling anything out personally. We are also going to be flying through the debris stream of 3i Atlas, whether it's dense or not that dense, in March and April. So that's all converging around that time. So I will keep you up to date on everything that's happening within our solar system with 3i Atlas and more on the channel. So if you'd like to stay up to date, then please subscribe. Again, I've been your host, Stefan Burns. Thank you all so much for watching. Wishing each and every single one of you well. Please take care of yourselves. I'll see you all in the next video.